so this is section 6, and it's called Honors Topic 1. It's like I said before the video started, my regular classes don't have to cover this. And then there's an Honors Topic 2 as well, which we'll also cover on the same video. Its title is Polynomials and Complex Numbers. And my target, what I want you to learn after this lesson, is how do you factor the sum of squares? So we already know how to factor the difference of squares, right? Difference of squares, perfect square minus a perfect square. We know how to factor a difference of cubes. We know how to factor a sum of cubes. But every time we've had a perfect square plus a perfect square, we've never factored it, okay? Because what we've been doing so far, we've only been dealing with factors that are real numbers or real factors. And when you factor a sum of squares, not a sum of cubes, sum of squares, your factors are going to be imaginary. They're going to be complex. Okay? So, for example, you know, if we were to factor 9x squared minus 100, we know that's a perfect square plus a perfect square, and we know how to factor that. But recall, if you don't know how to factor it, it has an identity. And the identity says when you have a perfect square minus a perfect square, that's difference of squares, you make two sets of parentheses. One gets a plus in the middle, one gets a minus in the middle. The first term in each set of parentheses is the square root of the first term. And the last term in each set of parentheses is the square root of the last term, right? That's the identity for a difference of squares. Okay, so we know we would make, for this example, we would make two sets of parentheses. Oh, first of all, does it have a greatest common factor? Because you always factor that out first. No. One gets a plus in the middle, one gets a minus in the middle. And what would be the first term in each set of parentheses? 3x. That's the square root of the first term. In the second set of parentheses, we put the square root of the second term, which is 10. If any of those factors can be factored any further, then we do that. But can they? No. We see they're both linear binomials because they have highest degree is 1. And remember, if it's linear, the only way it could be factored further is if it had a greatest common factor. If it doesn't, then it can't be factored further. Because a lot of y'all get stuck, like, I don't know how to tell if I'm finished or not. Well, you have to look at each factor and see, is there some identity that we can use on this? You know, is it a difference of squares, a difference of cubes, perfect square trinomial? Can I use t-chart divide and slide? Can I factor by grouping? Can I factor as a quadratic? You kind of have to go through that whole list. But if it's linear, you don't need to go through the whole list. If it doesn't have a GCF, you can't go any further. Okay? So we know how to do that. Well, a sum of squares I should have not need that S there. I should have said a sum of square binomials is a polynomial with two terms And each term is a perfect square. Well, maybe it should say a sum of squares binomial. Just sounds weird either way, I think. And it has an identity, of course. The polynomial identity for a sum of squares You're correct. Is. So we have ax quantity squared, so that means a perfect square, plus, open parentheses, by quantity squared. That's a perfect square. The identity says you make two sets of parentheses, just like with difference of squares. One gets a plus, one gets a minus, just like difference of squares. The first term is the square root of the first term. What is ax quantity squared? What's the square root of that? Just ax, right? That's the first term in each statement. So square root, or each parentheses. The second term in each set is the square root of the second term. What's the square root of by quantity squared? Just by. So you're like, well, what's different? Well, the difference is it needs an I. So I shouldn't have read that so fast. That's biy. And sorry about that. So it's ax plus biy times ax minus biy. That is an imaginary number. So basically you're going to have an I in that second set of parentheses. Okay? Because think about it. If I had, let me just do this on a separate sheet of paper. If I had 4x squared plus 25, that's a sum of squares, right? So if I tried to factor it like I would before, I would do two sets of parentheses. One gets a plus, one gets a minus. It'd be 2x, 2x, 5, and 5. If I tried to factor it like I did before. Okay, well let me distribute that and see if I end up with what I started with. 2x times 2x is 4x squared. 2x times negative 5 is negative 10x. Positive 5 times 2x is positive 10x. Positive 5 times negative 5 is negative 25. Two middle terms would cancel and you have 4x squared minus 25. Is that what we started with? No, so that doesn't work for sum of squares. All right, there's no two numbers that you can multiply together to get a times c would be 100 and add to get 0. It's not possible. But you can have two imaginary factors that multiply together to give you 4x squared plus 25. Okay, so that's why this has its whole different identity. It's different than difference of squares. All right, so let's give it a whirl. Let's factor 9x squared plus 100 using the identity. So we make two sets of parentheses. One gets a plus, one gets a minus. What do you think goes in the first set of parentheses? So 3x. I meant first term in each set of parentheses. What do you think goes in the second set? 10i. Boom. Done. Factor out a GCF at the beginning if there is one. There wasn't. So let me just check my work. I'm going to distribute to see if that actually works out to get 9x squared plus 100. Okay? So I will check by distributing. So I have 3x plus 10i times 3x minus 10i. All right, what's 3x times 3x? 9x squared. What is 3x times negative 10i? Negative 30 would be a xi, right? Because I have a 3x and a negative 10i. All right. What about positive 10i times 3x? Positive 30xi. Or it might be 30ix. And what about positive 10i times negative 10i? Negative 100i squared. Now remember what happens when you have an I square? We got to replace it with negative 1, right? Okay, and what happens to my two middle terms? They cancel out. So two middle terms are canceled. And on the end, we have to replace the I square with a negative 1. So we are subtracting 100 times negative 1, which that's going to turn into what? Positive 100. So we'll have 9x squared plus 100. Is that what we started with? Mm-hmm. Yes. So this is not our answer. I was just checking to see, well, how does that work out? How is this possibly going to multiply together to get 9x squared plus 100? It does. Okay? And that's about as difficult as it gets. And I think I should have put that I before the x. Unfortunately, I'm recording, and I made that mistake. No big deal. We'll fix it on the next one. Okay? You have a question so far? All right. Do another example on the back. We are going to factor 36x to the fourth plus 25y squared. Does that have a greatest common factor? No. Is it a sum of squares? We're used to saying sum of cubes, but this is not a perfect cube plus a perfect cube. Isn't it a perfect square plus a perfect square? All right, so it's a sum of squares. So we make two sets of parentheses. One gets a plus, one gets a minus. What's going to be the first term in each set? 6x squared. What's going to be the second term in each set? And remember, I said it backwards the last time. So we'll put the 5i and then the y. So 5i, y, which is the order it should have been on the last example. I just made a mistake. That's it. That's all you do. Easy breezy. Beautiful. Cover girl. All right, let's check this one out. X to the fourth minus 81. Is that a sum of squares? That's a difference of squares. Now, a lot of times, like say if you had the PERT or ACT or SAT or whatever, if they're just want you to factor, say it's multiple choice and you have a sum of squares and there's no answers with i's in it, then they're just looking for real factors, and so your answer would be not factorable, okay? But if they're particularly looking for all factors, real and imaginary, then you would see that answer in the list. But if they're just looking for real factors, it's going to say not factorable, which is what we've set up until this point because we've only been dealing with real factors, okay? So this is a difference of squares. So two sets of parentheses, one gets a plus, one gets a minus. What is the first term in each set? X squared, then what? 9. Okay, x squared plus 9, can that be factored? That's a sum of squares, right? What about x squared minus 9? That's a difference of squares. We have sum of squares and difference of squares. So this is sum of squares, and this is difference of squares. So we factor them pretty much the same except for that whole I thing. So for x squared plus 9, that's 2 sets of parentheses. One gets a plus, one gets a minus. What's the square root of the first term? What's the square root of the last term? 3i. And that one didn't have a variable in the second, right? So just 3i. And then we can still factor x squared minus 9. 2 sets of parentheses. One gets a plus, one gets the minus. What is the square root of the first term? It's the square root of the last term. And no I on that, right? Those are real factors. There you have it. Before today, we'd have just factored x squared minus 9 further. One more, and then we're going to move on to the honors topic 2. Let's factor 16x to the 6th minus 49. I meant to say plus 49. What is that? Sum of squares. Do I have a greatest common factor? No. And yes, it is a sum of squares. So 2 sets of parentheses. One gets a plus in the middle, one gets a minus. What's the first term in each set? 4x cubed. And what about second set? 7i. On the first one, is that a sum of squares? Is it a sum of cubes? What about the second one? Is that a difference of cubes or squares? No. Is there anything else we can do? No. That's it. Y'all got it? All right, that's all there is to it. Now, section 6 honors topic 2. Little different. It's section 6 honors topic 2. It's called the binomial theorem. And the target is, how do you expand a binomial to the nth degree using the binomial theorem instead of distribution. All right, so in my first example, we are going to expand a plus b quantity cubed just the way that we already know how to do. By expanding it, I mean we're going to write it in standard form. It's in factored form right now. We're going to write it in standard form using distribution. All right? So doesn't a plus b quantity cubed, doesn't that mean a plus b times a plus b times a plus b, right? And remember, I told you, when you are trying to distribute, don't try to distribute all of those at once. It's not going to work out right. So just group 2 of them together at a time. So I'll group my first 2 binomials together, and then my second. I'll come back and pick that, or the third. I'll come back and pick that one up at the end. Now, wouldn't this be a perfect square trinomial? Isn't there an identity instead of distributing that I could just write it in standard form without having to distribute? I think it was topic 4 we learned that. Now you could go ahead and distribute the whole thing if you wanted to, but it's not necessary. If I have a perfect square trinomial, to use the identity to get it in standard form, I take the first term in each set and square it, multiply what's in the parentheses together, and then double that. So a times b is ab doubled is 2ab, and the sign is the sign in the parentheses. And then to get the last term, it's always plus on a perfect square trinomial, and you square the second term in the set, so that would be b squared. Again, if you forget all that, distribute it all out. The two middle terms are going to be the same. That's why when you add them together, it's doubled because they're identical. Okay? Alright, but I don't have an identity for this, so I will have to distribute. Alright? And I'm trying to save some paper, so I'm not going to make more space and do all of my different colored arrows. So just be careful. What's a squared times a? A cubed. A squared times positive b plus a squared b. Alright, let's move to the 2ab. Positive 2ab times positive a. Positive 2a squared b. Positive 2ab times positive b was 2ab squared. Alright, move to the b squared. Positive b squared times a plus b squared a. Positive b squared times positive b plus b cubed. There's a way that we can do this. I can go from a plus b quantity cubed to the standard form without any of that in the middle stuff. I can just go one to the other. Do you want to know how? No? Good, because I'm going to tell you how. It's kind of cool. Okay, first of all, do you notice a pattern? Do you notice my first term had a cubed and then the second was a squared? Did I make a mistake here? A cubed, a squared b, 2ab, I'm a little confused right now. A cubed. Oh, we didn't combine like terms. Duh, that's what the problem is. Do I have any like terms in here that I can combine? Okay, so we got to do that. It's kind of important. All right, so a cubed, is there anything I can combine it with? No. I'm going to kind of cross it out. All right. How about a squared b? Yeah, I've got a squared b plus 2a squared b. Anything else? What does that make? Plus 3a squared b. Mark those out. 2ab squared. Do I have another b squared a? And that's just written backwards, but doesn't it mean the same thing? So that would be plus 3 what? ab squared. Yeah, something's still not right. Plus 3 ab squared. No, 2 plus 1 is 3. And remember, we're adding them. So ab squared, because that's ab squared, right? We're not adding any exponents or anything. And then plus b cubed. Okay, this makes more sense. So now notice, my first term had a cubed and then a square, a, no a's. So it went from 3 degrees, 2 degrees, 1 degree, 0 degrees, right? My first term didn't have any b's. The second term had b to the first, and then b to the second, and b cubed. So the second variable, did none in the first, and then it went up by 1 degree, correct? Okay, pattern. See that pattern? You think it's always going to happen? I don't know. All right. Any binomial raised to a power comma, we can start to see a pattern develop. the binomial coefficients follow a pattern known as Pascal's triangle. Y'all ever heard of Pascal's triangle before? No, Miss Rayleigh, we haven't. Okay. To find each subsequent coefficient, comma, find the sum of the two closer terms in the row above. All right, so Pascal's triangle starts with a 1 at the top. And the next row just has 2 1s. Okay, you always have a 1 on the outside of the sides, on both sides, has a 1 every time. Okay, so my next row, I have a 1 on the outside, then I add the 2 numbers together above, that gives me a 2, and then I put a 1 on the outside. My next row start with a 1. These 2 numbers, 1 plus 2 is 3. 2 plus 1 is 3. Put a 1 on the outside. My next row starts with a 1. 1 plus 3 is 3 plus 3 is 3 plus 1 is, put a 1 on the outside. The next row, start with a 1. 1 plus 4 is, 4 plus 6 is, 6 plus 4 is, 4 plus 1 is, put a 1 on the outside. The next row, start with a 1. 1 plus 5 is, 5 plus 10 is, 10 plus 10 is, 10 plus 5 is, 5 plus 1 is, put a 1 on the outside. And you can keep going as long as you want to go. Okay? This is the pattern that you're going to use for the coefficients when you're squaring a binomial. Okay? So, notice this column right here, I've got 2, 3, 4, 5, 6. See how that works? This is the row you would use if your binomial is being squared. This is the row that you would use if your binomial is being cubed. This is the row you would use if your binomial is being raised to the 4th degree. This one is to the 5th degree. This one is to the 6th degree. These are the coefficients of each term. Okay, so like look at that example above, a plus b quantity cubed. That had 3 degrees, right? So we would use this row for our coefficients, the coefficients in that term. So our coefficient should be 1, 3, 3, 1. Let's go look at it. Our coefficient was 1, 3, 3, 1. So if we know Pascal's triangle, and really you don't have to memorize it, you just have to know how to create it, right? If you know how to create it, you don't need to memorize that. And that will give you the coefficients that you're going to need in your final standard form. Now, the variables also follow a pattern, which that's what I was pointing out. So if you know the pattern of the variables and you know Pascal's triangle, that tells you the coefficients. I don't have to go through all of this work. I can go from a binomial being cubed to standard form without any of this middle stuff and all of the craziness that I could make mistakes. All right? So, backside. The variable terms also follow a pattern. In the form of a plus b quantity raised to the nth power, comma, the a term will start with the highest exponent and decrease by 1 to 0. On the last term. The b term will start with 0 and increase by 1 to the highest exponent term. Example. Use the binomial theorem to expand a plus b quantity raised to the 4th power. Okay? Alright, so a plus b raised to the 4th. If you didn't know Pascal's triangle and binomial theorem, you'd have to do a plus b times a plus b times a plus b times a plus b. Y'all had one like that in your homework the other night where I told you to write, you had a 0 of -1 with a multiplicity of 4. Remember, you had to group the first two terms together, multiply all that out, remember, and then multiply all that out, get it in standard form. So we're going to do that, but just using Pascal's triangle. So if you have a binomial, 2 terms, raised to the 4th power, it doesn't work on a trinomial, or 4 terms, quartic, works on a binomial. So 4th degree, we know that our coefficients are going to be 1, 4, 6, 4, 1. I'm just going to write that on the side over here. 1, 4, 6, 4, 1. And if you wanted, don't get confused, you could write the whole thing up to that point. Also kind of helps you remember how you got there. Alright, so this is 4th power. So, I like to give myself enough room. I always start with the coefficients. So, I've got 1, and this is plus, alright, so everything's going to be a plus. 1, 4, 6, 4, 1. Give yourself plenty of space. Alright, so the first term is going to start with however many degrees that you have that you're expanding it to. So 4. So it would be a to the 4th, a cubed, a square, a to the 1st, a to the 0. Which, what is a to the 0? 1, right? So we don't really need that, but it helps keep everything in order, and then we can go back and clean it up. Okay? The second term in the parentheses, it starts at 0 in your first term. So that would be b to the 0, b to the 1st, b squared, b cubed, b to the 4th. All right? And this was positive, so everything's going to be positive. Okay, so now let's clean it up. What is 1 a to the 4th b to the 0? Just a to the 4th, right? B to the 0 means 1. 1 times a to the 4th times 1 is just a to the 4th. For positive 4a cubed b to the 1st, it would be plus 4a cubed b. We know we don't need to write to the 1st. In my next one, there's nothing to clean up. Plus 6a squared b squared plus 4ab cubed plus 1 times a to the 0, that's 1. So 1 times 1 times b to the 4th is just b to the 4th. Without doing all of that multiplication, we have it in standard form. It's kind of cool. I don't know what Pascal had going on that he had all this time to figure out this triangle thing, but it's pretty neat. Is everybody cool with that? Done. We're not factoring. It was already factored. We're put it in standard form. Let's look at another one. Let's expand. We're still using binomial theorem, just not writing that. X plus 3, quantity raised to the 5th power. So if I didn't know about Pascal and his cool triangle, I would have to do x plus 3 times x plus 3 times x plus 3 times x plus 3 times x plus 3. Group it in groups of 2, distribute all that out, put it all together, combine like terms, all that stuff, all right? But we know Pascal's triangle and the binomial theorem. So this up here that was for 4 degrees, right? So we don't even have to look on the page before. If I want 5 degrees, it's going to be 1, 5, 10, 10, 5, 1. This was 4th degree. This would be 5th degree. Y'all cool with that? And these tell us are what? What are these numbers? Coefficients. And we have 6 of them. So leave yourself some space. So we have 1, 5, 10, 10, 5, and 1. Oh, and on our Pascal's triangle, we stopped at the 6th degree. That just keeps on going. So if you had 10 degrees, you could just keep that triangle up all the way till you get to the one that would be 10th degree. I'm not going to give you one like that, but I mean, it doesn't just stop at 6 because that's where we stop. You can go on as long as you need to. Okay? All right, so our first term is x. So what are we going to write here? X to the 5th. Now, if that was a number, if that was like 2x, we would have to write 2x quantity raised to the 5th. Okay? So we have x to the 5th, x to the 4th, x cubed, x squared, x to the 1st, x to the 0. Then we look at our second term. It's 3. Okay, it's not a variable now, it's a number. That's okay. So we'll start with 3 to the 0. And this is plus, so everything's going to be plus. We don't have to worry about any negatives. And this would be 3 to the first plus, this would be 3 squared, 3 cubed, 3 to the fourth, 3 to the fifth. I feel like I keep zooming in, and when I look up, it just does not seem very zoomed. Whoa, whoa, whoa. Okay, do you think I'm going to be able to leave it as 3 squared and 3 to cubed and 3 to the fourth? No. Okay, so let's clean this up. 1 times x to the fifth times 3 to the 0 is what? Just x to the fifth. All right, so here we have 5 and 3 to the first. What is 3 to the first? And I can multiply these two together, right? Because it's going to be a coefficient. So that would be what? 15x to the fourth. Plus 3 squared is 9 times the 10 gives me 90x cubed. So when we look at this one, it's not going to match the coefficients that we had in Pascal's triangle, is it? No, and that's because we had a number here, not a variable. All right? So where are we? Over here. What's 3 cubed? 27 times 10? 270x squared. Awesome. 3 to the fourth? 81 times 5? It's what? 405. Close. X. Plus, anybody know what 3 to the fifth is? 243. Nice. So 1 times 243 is 243. And x to the 0, am I going to need an x out there? No. All right. So that one looks a little different. These coefficients don't match up because we had a number here and not just two variables. Okay. Let's do one more that has a minus sign in it, just so you can see, okay, well, what do I do if it's negative? You're still going to put pluses in between, but that second term, if this is a negative, that will change the signs when they need to be changed. So you'll still write pluses, and then if you have to do a plus positive times a negative, that's when the sign will change. Let's expand. X squared minus 4 quantity cubed. So we know we're going to use the 1, 3, 3, 1, right? That was for the third degree in Pascal's triangle. For difference of squares? Yeah. Perfect square minus perfect square? Well, no. You could do it for, like if you had a perfect square trinomial, like x plus 2 quantity squared, that makes a perfect square trinomial. But a difference of squares would be like x squared minus 2. If it was then quantity squared or quantity cubed or quantity raised to the fourth, you could do that, yes. Okay, all right, so this one's going to be a little bit weird because this x is being squared and we have the number, but just follow the pattern, take it one step at a time, all right? So we know our coefficients are 1, 3, 3, 1. Our first term, so our degrees are 3. It's our highest degree. So our first term is going to be raised to the third power. So it has an exponent. It's going to have another exponent. So x squared will be raised to the third power. And then x squared will be raised to the second power. I should have written with a thinner pen. And then x squared will be raised to the first power. And then x squared will be raised to the 0 power. Okay. Now, when I do the second term, I'm going to take that negative into account. All right. So in the first set of parentheses, we start at 0 for the second term. So that's negative 4 raised to the 0. Okay. We can put a plus here. And then we have negative 4 raised to the first, then a plus. Negative 4 raised to the second, plus negative 4 raised to the third. So these get a little bit more complicated. All right, in my first term, what happens when you have an exponent that has an exponent? What's that rule? It's called power to a power. You multiply them. Keep the base, multiply the exponents. Okay? So x squared quantity raised to the third power is x to the 6th. So we have 1 times x to the 6th times what's negative 4 times 0? Not 0, but 1. Anything raised to the 0 power is 1. So basically, we just have x to the 6th for our first term. Right? All right, so we don't have to try and do all of this in the same time. We could break it down if we wanted to. Okay, what's negative 4 to the first power? Just negative 4 times positive 3 is negative 12. And what's x squared quantity squared? X to the 4th. So we've got our first term taken care of. Second term over here. What's negative 4 quantity squared? 16 times, and it's positive, right? Times positive 3 is plus 48. X squared raised to the first power? X squared. So we've got this third term taken care of. Over here, 1 times, what's x squared raised to the 0? Just 2 times 0 is 0, right? So it's going to be x raised to the 0, which is 1. Anything raised to the 0 is 1. Negative 4 quantity cubed. First, it's going to be negative 4 times negative 4 times negative 4. So it's going to be negative, and 4 cubed is 64. Boom. Pretty cool. We have room for another one. Do we need to do another one? Because I'm going to give you some work to do.
I don't have any room.
You don't have any room? You see the pattern? Do we need to do another one? You want me to? Okay. Let's do b plus 2 quantity raised to the 5th power. And like the last one I gave you, I won't give you one like the x squared on your home, or should, but I just really want to know that you can do the process, like you know how to do the process. All right, so 5th degree on Pascal's triangle, our good gracious, our coefficients will be 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So we start. The first term is going to have how many degrees? 5. It's whatever the exponent is outside the parentheses. So b to the 5th. And I do my first term all at once, and then I go back and do the second term. I don't try to do it all together because then I'm going to make a mistake. You might be able to. So b to the 5th, b to the 4th, b cubed, b squared, b to the 1st, b to the 0. If you want to go ahead and put pluses in front of each term, that's fine. I know since there's not a minus, I don't even have to worry about any negatives in there. Now for the second term, we start with the 2. And what will its exponent be in the first term? 0. And then 2 to the 1st. And then 2 squared. 2 cubed. 2 to the 4th. And 2 to the 5th. Is everybody cool with the pattern? All right. Pattern's the easy part. You just have to make sure when you simplify it correctly. Don't make any mistakes. This will be on your test. Okay? All right. So 1 times b to the 5th times 2 to the 0. What's 2 to the 0? So basically that's 1 times b to the 5th times 1. What's that? b to the 5th. Plus 2 to the first is times 5 is, so that's 10b to the 4th, plus 2 squared is 4 times 10 gives me 40b cubed, plus 2 cubed is 8 times 10 is 80b squared, plus 2 to the 4th, 16 times 5, 80. So it's plus 80b. All right. And 2 to the 5th, 32, times b to the 0 is just 32, right? B to the 0 is 1. And that's it. So that saved a lot of work. B plus 2 times B plus 2 times B plus 2 times B plus 2 times B plus 2. Bam, just like that. We did that in probably less than 2 minutes. Anybody have a question? Comments? Concern? Aren't y'all glad you were here today for this lesson? But that's why I recorded it, so people at home, because that would probably be hard to figure out without hearing it, just by copying notes down. All right, so I will pause the video and give you your assignment.